Okay, we're going to try to get started now. I'm good if that's okay with you. Yeah. Well, I think I can say good afternoon. We have a very interesting group of panelists here. When Michael originally spoke to me about participating in this conference, he asked me if I wanted to do a presentation. And after a little bit of arm twisting, I said yes, and this either evolved or devolved into being a moderator, which is kind of a funny word. You think of more stirring things up rather than smoothing things over. So let's think of it as a stimulator rather than a moderator. In that vein, Michael has given me the opportunity to do a short presentation. But before that, let me say a few words about our panelists. There's, of course, the longer descriptions and bios in the back of the program. We have Jan Knippers, an engineer, PhD from the Technische Universität in Berlin, started his own firm and has an office both here in New York and in Stuttgart, and is very interested in glass reinforced materials, something I'm quite interested in as well. And our own Craig Konyk, an architect here in New York City, also started his own firm and has participated in many studios in this school, both in preservation and in the architecture part of the school. So we're very pleased to have Craig here as well. Werner Preusker, as Michael mentioned, from Bonn. He's an attorney, the managing director of the PVC and Environment Institute, working on a very important, pervasive, and for some consider problematic material. So we'll be very interested to hear what Werner has to say. And then finally, Rita Schenck did her PhD at the University of Rhode Island in oceanography, and is the founder and executive director for the Institute of Environmental Research and Education. Was also a industry environmental manager with GE, which you might consider they get an honorary PhD for that as well, considering some of the problems GE has had over the years. So Michael was worried about going back beyond 1950. I'm going to actually take us back to 1490 in my presentation. So I'm going to start here. Just to remind us of the importance of being flexible. You might consider that both a material and a human condition. I'm going to be talking about how you repair marble with various pinning materials and how that's been done in history and how we've been looking at it today as a touchstone for this subject. This is a sculpture by Tullio Lombardo from about 1490. And it remained in this similar condition until about October 9th, 6 p.m. in the evening, 2002, when its pedestal collapsed and was fractured in most of these positions here, with hundreds of other fragments strewn about the floor. I'm in historic preservation, so we need to do a little bit of history first. So I want to look at some of the materials that have been used to hold things like our bones in the same sort of way. This is the bones of our sculpture we're trying to put back together. We've used wrought iron, cast iron, soft steel, historically mostly encased in lead in outdoor environments for the corrosion protection. Copper, bronze, and brass as we moved into the Bronze Age. And then by about 1840, when stainless steel really came into the picture, everyone has used stainless steel for the repair of stone, and in particular marble. A few examples: once nickel silver was discovered as an alloy in the 1890s. This has been used occasionally as a pinning material, and more recently titanium, a good example is the Parthenon, because of its corrosion resistance and its similar thermal expansion properties to marble. And then finally, plastics and composites, what we're talking about here today. So this is actually a nice transition from Michael's conference on metals last time to plastics, because I'm going to look at both metals and plastic materials for pinning sculpture. What we're interested in really is this concept of modulus, that is inversely, how flexible is a material and how does it behave elastically, as engineers and material scientists might talk about it. And then how do these things fail? How do they fail in catastrophic circumstances? These are things that are very important to us in the repair, not just of marble sculpture. This has lots of applications in an architectural context as well. One of the things we do, we go to the literature and we say, let's find some numbers about what are the different moduli of the different materials. How stiff or how flexible are various things. Do we have a pointer here? How does this work? red. One of the things that's really striking to me about this list were a lot of plastic materials, of course, fiberglass. Here's marble. This is the modulus of marble in gigapascals. Here's the modulus of stainless steel. Of course, this is drawn from the literature, and the thing that's striking is how different are these moduli. So one of our questions was, why would you even think about using this kind of material in contact with marble as a repair strategy? And then, of course, we're interested in the actual modes of failure. The typical engineering diagram would show a stress-strain curve for a brittle material, very little plastic deformation before failure, whereas a good ductile material, we get a tremendous amount of plastic deformation before the material actually fails. This is something we like about a pinning material, so that addresses the question why you might even look at metals as a pinning material. So one of the things we did is, rather than rely on the literature, we actually went and took all of these materials we might be using for a repair strategy and perform a three-point bend test to find their flexure modulus. Because there's a whole range of moduli, compressive, tensile, shear, etc. So we thought the flexure modulus was the one that most closely associated with what our strategy was. And in measuring those flexure moduli for 316 stainless, we got 72 gigapascals. And there's the deformation. This is wonderful plastic deformation without failure. This is Carrara marble. By the way, this sculpture is made from probably the most beautiful and uniform piece of Carrara marble I have ever seen. Here's the flexure modulus of Carrara marble, 22 gigapascals, and of course it fails brittly. So we have two different failure modes in materials we're trying to put together, and very different moduli. Here's the failure of Carrara marble, demonstrating its brittle failure. Here's titanium. Well, we've dropped down the flexure modulus, something a little bit closer to what we might need for marble, but still a little high compared to 22, and of course good ductile and plastic deformation. Aluminum dropped maybe a few gigapascals lower. Aluminum we might not want to use because of its thermal expansion properties. Here we now get down with carbon fiber, 30 gigapascals versus 22. This is a very interesting kind of failure mode. If you kind of blur your eyes a little bit, it really looks like ductile behavior as it would be with a metal. Of course, what's going on microscopically here is the failure of fiber by fiber by fiber, not the kind of plastic deformation that occurs in metals microscopically. But nonetheless, it's not really a brittle material, which is something we might like for a pinning material. Here's the kink behavior, the kink failure that occurs in fibrous materials. The plastic matrix fails, and then fiber by fiber gets broken. And again, just to emphasize that point, this is sort of looking like ductile behavior in this fiber-reinforced material. And maybe Jan will have more to say about that in a few minutes. And now we look at fiberglass. Here's the flexure modulus at 20 gigapascals. We're right in the range now of what we might want for Carrara marble, and we have a similarly pseudo-ductile behavior and the kink behavior you see in fiberglass. And just to look at some of the plastics themselves, unreinforced with fibers, they are brittle materials. They're not very stiff materials. This is very, very low flexure modulus, but boom, they break, they snap at the end. So just using a plastic pin by itself is not a good idea, both because of the low modulus and the brittle failure. Those are acrylics. Here's epoxy resins. By the way, that was a thermoplastic material. This is a thermosetting material that we just heard from Lydia. So one of the things we then did is let's make some full-scale mock-ups of all these broken joints and then press them to failure and see what kind of results we get. So we actually took large marble cores, mimicking the breaks in some of the joints, these shear joints, glued them with the different pinning materials, and then pressed them to failure. And if you do that with stainless steel, this is what you get. You actually destroy the marble sculpture in the process of a catastrophic failure of the system. This is exactly against the typical principles of conservation, where the repair is supposed to fail and not the parent material. And yet, over and over again, we've been using stainless steel for repair of marble and other stones in both indoor and outdoor environments. Here's carbon fiber. We shear eventually we shear the fibers, and the whole joint is completely intact. We do get a few cracks with carbon fiber because of the modulus is slightly higher than marble. And here's our fiberglass. Again, we just shear that pin. Very, very high force, by the way, that's required to actually bring about failure. But nonetheless, none of that is transferred, at least in these experiments, into the marble itself. So if our sculpture falls off the platform yet again, and it breaks at the arm, hopefully the two pieces will be intact. We did some other full-scale mock-ups for other joints using 2 pins and actually gluing the joint, fracturing the joint, gluing it back together to mimic the strategy we would use for repairing the sculpture. Again, if we do that with something like titanium, which had about 35 gigapascals modulus, we actually cause the core to fail. Carbon fiber, again, a little too high on the modulus, so it hangs in place too long while you're stressing it and breaks the marble. And again, fiberglass was intact, not intact, but the marble is intact after you put a catastrophic force on it. Just want you to focus on this number. This is 940 psi. The maximum stress on the sculpture that we did by doing laser scanning is about 120 psi. So these are very strong joints. But what was very interesting to us at the kind of the end of the day was we just glued 2 of these pieces of marble together with, by the way, thermoplastic a resin, an acrylic resin, and notice what the force of failure was of that joint. This is 9 kilonewtons higher than the pin strategy. The pins actually introduced, as we learned from doing finite element analysis, the pins actually introduce stress concentration around the holes and actually cause the thing to be more susceptible to breaking than if you just glued it together with a thermoplastic resin. And just to address the final point that Michael talked about how long do flexible materials last, we finally, after looking at all of these pinning strategies, have decided to simply glue the joints back together rather than introduce any pins. In part, we learned that drilling a hole in a piece of marble to introduce a pin brings about a tremendous flaw in the system, and that is very susceptible to breaking at the end of the hole where the drill hole was made. So we've decided and explored a whole range of different glues to put this back together. These are all Röhm-Haas designations of various acrylic block copolymers. And we wanted to determine their creep life. That is, if you set them in place for a long period of time, are they going to stay in that place without any pins? So notice these are in years, and my colleague Carolyn Ricardelli was showed this slide to an audience with people who were not too familiar with material science or creep. So she said we should put some other things in for people to get an idea of how long these things actually last. So I just want to end with a few acknowledgments. Some of this work is our thesis work by our students, Christina Muir and Andrea Buno. So our students are, as Teo said earlier, are generating a tremendous amount of good work. We learn as they learn. At the Metropolitan Museum of Art, Carolyn Ricardelli and Ron Street. When I originally started this project, I wasn't here at Columbia, so we did all the material science work with Princeton. We're trying to change that now. And a lot of the finite element work was done by CIE associates, Patrick Cunningham. And again, I would particularly like to thank Michael Bell for constantly bringing the HP part of the school into this arena. And this is an important connection that we will help, we certainly gain from, and hopefully the school does as well in this network growth pattern. And Mark Wigley, who has very much supported the preservation program, and in particular the conservation work that we do in our lab. So thank you for your attention, and I'd like to bring our first speaker up. John, please take over.
Okay, thank you for the introduction. Thank you for the invitation to this conference. I I am as well teaching students of architecture and doing research since nearly 10 years now on fiber-reinforced plastics at the University of Stuttgart. I'm also partner in an engineering firm. We design all types of structures. So we have today the tendency towards more and more complex geometries, free-form shapes in modern architecture. But it still is an issue to materialize these forms. And that's the field where I'm working on. That's my contribution to the whole story. Yeah? This was initially designed by the architect as an aluminium structure, cast elements here, extruded elements here. But it turned out that they could not reach the required quality of the surface and accuracy of the shape. So the contractor came up with the idea to switch to fiber-reinforced plastics. And that's, I think, one of the main issues today. Fiber-reinforced plastics are the materials to materialize these free-formed and complex geometries. We were doing all the, first, there's a remarkable contrast between the elegance of the form and the technology of the design tools and the way these elements are actually manufactured. And that also holds for boats or for Formula One race cars, because they're mainly manually made. Yeah? It's a handmade process, which is very, very simple and does not really reflect the technology or the technical appearance of the elements. Yeah, you can see that they put the fibers in a form and so on. So this 5,000 elements were produced in various small shops all over Europe. We did all the engineering for this FRP lamellas, and I just want to show you a few technical slides just to show you what are the issues for us as engineers. You can see here the red line is the temperature of this specimen here, and the other lines show the deflection under constant loading. So what you can see is that a temperature which is reached at a normal warm summer day, the deflection is under constant load increasing. It means it's a kind of creep effect, which is very difficult to handle for us as engineers. Yeah. And the second issue here was the coating of the elements. You need a coating to achieve this high-tech appearance, but also to protect the polymers from UV radiation if you want to achieve durability. And we tested here the propagation of cracks at certain levels of stress and strain. So these are the main topics we were working on here. And this is probably the first office building of this size where FRP was used for the envelope, but we will definitely see more and more buildings which go into this direction. Just one more very typical application of FRPs in today's architecture is this building that we have worked on as structural engineers in Mainz. Yeah, there are these 3 columns which initially supported a rooftop terrace, which was then dropped during the design process due to cost reduction reasons, but the 3 columns remained and remain there as room enriching, room dividing elements. I think this is a very, very typical application of FRP in today's architecture. And again, there's a difference, remarkably contrast between the beauty of the form or the elegance of the form and the way the things are actually put together today. Yeah? It's exactly what Greg Lynn mentioned in his talk yesterday evening. This here is 12 meters. This is only FRP, yeah, just form and material. It's a much simpler form than we've seen yesterday evening, but it's just form material. But when you come to the point where you have to bring the elements together to scale it up to the size of a building structure, then you have to go back to very traditional connecting elements, steel and bolts and so on. Yeah? So I think, if I understood you right, you said yesterday evening that design is not depending on scale or form or geometry. But when you come to the point where you want to materialize the things, of course, the scale of the whole thing is very important. Yeah, okay, so these are very typical applications that we see very often in today's architecture. I want to come to the point, what does the usage of plastic mean for us as engineers or architects or designers? For me, there's a specific, a very large contrast between working with steel or wood, for example, and working with plastics. Because when I design a structure made of steel, I take a material which has given and defined material properties. Yeah? I can look in a book and see what are the material properties of the steel beam. And that's completely not the case for any kind of plastics. There are so many resins and fibers and aggregates and fillers that could be put together in endless ways. So that means when you work with plastics, you have to design the material itself before you start to design the building or the structure. That's what plastic is cooking, or something like this we said yesterday evening. To illustrate this, I show some pictures of seminars that we do with students, just to show that it's very easy to combine all these material components when you work with plastics in endless ways. Yeah? So what we do with students is we build boards, sandwich boards with different types of cores, which form different material properties and different textures, and we let them laminate LEDs in the plastic boards, or these are optical fibers. And if our students can do this on a weekly Tuesday afternoon seminar, yeah, we as professional engineers and architects could use this technology also in our design projects. So the working with plastic means design of the material itself. And that's a big difference to all other tasks or materials that I know. So what are the major obstacles to a broader application of plastics in architecture? For me, there are two main issues. The first is the ecological issue. So what we need are recycling technologies for thermoset resins, we need recycling networks, we need biodegradable materials, we need resins made from agricultural waste, and so on. This is one issue which goes very deep into material science, and I'm not really the expert on this. And the other point is the thermal behavior of plastics. Yeah? Plastics are made from oil. That means they are combustible, inflammable. That is a very big issue for many applications in building structures. Okay? So we did also research on this, and you can see here on one side the temperature, on the other axis the decrease of stiffness, and as I said before already, on a warm summer day, the stiffness already is reduced by 20%, and in case of a fire event, you are within seconds here at temperatures of this range, and you lose all the stiffness of the material. So even if you are successful in preventing the material from inflaming, you will lose the stiffness when the temperature increases. And this is, of course, not possible for all load-bearing elements. This is one big issue. And we have a project in the moment on our desk where this was a big discussion. This is the Opera of Berlin, which the auditorium was rebuilt in the 1950s, and the acoustics of this auditorium are very, very poor. So all the tourists come to Berlin, go into the opera, and are very disappointed by the experience they make there. So they spent now millions of dollars or euros to improve the acoustics of this auditorium. And what they are doing is they are increasing or lifting or raising the entire roof of the opera and adding this reverberation gallery to improve the acoustic behavior of the room. But this big action shall not affect the overall perception of the room very much. Yeah? That's why they want to put in this grid here, which forms a visually closed ceiling that allows the sound waves to pass. Yeah? That's what they want to do. And this is, after spending, I don't know, 100 millions of euros, this is the only visual remaining which stays there after this big effort. And that's why this is, of course, a very, very important element for the architect. Yeah? and that's why we discussed hundreds of options to design and fabricate this grid. Timber, woven timber lamellas, aluminium elements, but only with plastics we could achieve this appearance of this artificial appearance of the grid with varying thickness and width of the grid members. But how to do this in this surrounding where combustible materials are absolutely impossible? So we had to talk to all European industries in chemistry to finally find a material which is used until now for the interior of ships. Yeah? And we will cast this as a specimen that we did at our university lab. We can cast this in a way that we get this grid. So this is a phosphate binder, a mineral binder, which has similar properties, mechanical properties, and allows for similar processing technologies as polyester resin. What I want to say is I'm a structural engineer, I'm not a material scientist, but when I want to do structures with polymers, I have to go very, very deep down to the basis of material research. That's what I want to say finally. So and only with plastics we can achieve this very nice structure. I also want to say that there are some new applications, new structures, which are only possible if you use plastics. And I want to show you one project, research project we are working on since 2 years now. Plastics show the properties that they have a very high breaking strength compared to other materials, but a very low stiffness compared to other materials. Yeah? What you can see here, the pole jumper, he's using these properties. Usually, this is not very good for all structural applications, but we want to functionalize it for pliable structures, for deployable structures without hinges and bearings, yeah? Without tectonics. And where you can find this is in nature. Yeah? You can find in biology very many structures who only work with stiffness, changing stiffness. Can you start the other one also? The other one. Where you have structures which work only with stiffness, with change of pressure in the cells and fibers, which have no mechanical tectonic devices. Yeah? And we had a look at this and tried to look at elements like this. Yeah? We teamed up with a team of biologists from Freiburg. They investigated this flower, bird of paradise flower, which is pollinated by a bird, which means it has a quite stiff perch here, and when the bird sits down, the perch bends down, and this bending causes its sideways flapping of the lamina. And they are investigating this, and we are trying to transfer this into an engineering model. Yes. At the first look, at the first sight, it looks quite complicated, a lot of strands and fibers and laminas. When you go step by step further in understanding the mechanism, it ends up with a very simple mechanism. Yeah? You can see here a stiff backbone, a soft lamina, and when you bend it down, the lamina flat sidewards to avoid loading the stress of the material. Yeah? We as engineers, and there are some engineers here, know this as torsional buckling, failure mode, but I was trained my whole life as engineer to avoid this failure mode. And nature is using this as an active mechanism. And this switch of the perspective, that is an important thing or a good thing about biomimetic research. So we transferred this to a sun shading system. You can see prototypes made of fiber reinforced polymers. So here we have a rod which induces a bending in this backbone, and this bending leads to the sideways flapping of the fiber reinforced polymer lamellas. In the next step, we will replace this by self-actuating backbones which react to change of temperature or UV radiation. And then you have a system without any joints and bearings or any traditional engineering elements. Okay, so we did, you see here, we still have to work on this. These are very early prototypes. When you bend the backbone, you get the sideway flapping. Oh, give me some more minutes, please. 2 more minutes. So we go more and more to complex geometries. We try to introduce this into building construction. And what do we need this for? Because we have this glazed complex geometries. Sun shading of this element is very difficult. You need a lot of technical tectonic elements here, which is very complicated. And these elements, they can be adapted in size and geometry to any surface because it don't have a straight axis of rotation. Okay? And we proposed this also for a competition that we did last year with Asymptote Architecture here in New York, because these elements can be applied to any geometry. 2 minutes, please. Okay, this is a project that we have now on our desk in Korea, South Korea. We also use elements like this. This was a proposal from the architect, who are young guys from Vienna. And they won this open competition and proposed this kinetic facade, but did not know how to do it. So they came to us, and we told them how to do it. We proposed this system, very simple, and 2 fingers form a support, and the 2 other fingers are pushing inwards, and this causes this bending of the element. And these type of elements, of structures, are only possible using the elasticity of the material. No other material would allow for these elements. Yeah? I skip this, just show you the final image. So that's what I want to say. There's a lot of potential in the material, which is not really exploited yet by architects and engineers. And that can only be done by understanding these materials, by using them in new ways. Thank you.
First, I want to thank the Vinyl Institute and Columbia and Mark and Michael for having me and organizing this. I want to talk about what I think is probably on everyone's mind is that there's a kind of discontinuity, a kind of the paradox of plastic. What other material that can be engineered to last 400 years would you freely throw away? Seems to be the beginning of this sort of discussion. The fact that plastic is seen to be a future material, but readily degrades, so it could never really find its way into the future, is maybe another idea that I'm sort of interested in terms of the thematic that we've been placed in. I also have a paradox with the presentation because I'm going to do a plastic part and a paradox part, so we'll do the plastic part. I guess I do the plastic part. These are some projects that are some theoretical, a few built, that deal with plastic that we've done over the last 10 years. This was something called Millennium House. It was a seminar by Keller Easterling. I think we'll be speaking later to this in this symposium. And it was like a blue sky. So the idea is that maybe there's no house, but a surface, and a surface that is pliable. And so the rooms are somehow made by deformations of the surfaces. And again, this is sort of the future idea of plastic. Bedrooms would just occur, multimedia would just occur, push a button, very utopian, very easy to render. I want to be honest. Some of these are early ones. This is a house where there's no rooms in the house. The idea is the plastic there's some flexible material, would extend into the suburban landscape, and it's a perfect model for teenagers. If any of you have them in your house, you know what I mean. And so the idea that you can enjoy the landscape and actually have that evolve was the second idea we had for the Millennium House. This was an exhibit we did about the same time called Thin Skins, about thin structures and art specifically dealing with that. Ernesto Neto, economist Pierre Ranzoni, Warhol, Ellison, Bibliothecarist were all included. And so we, as designers, we've been doing work for the AXA Gallery, designing many times. We always try to transform the space. And so this was using vinyl sheets that would actually inflate away from the wall and divide the space up into different places, little compartments. So the walls kind of just breathed or inflated. And they were PVC panels with a kind of texture already on them. This was a competition. I have to really apologize for this because it was for San Francisco, and I'm sorry. I think there was someone in our office, but it was for a competition, very thin site rebuilding after the earthquake that opened up these kind of perimeter sites because of the collapse of the highway. And so we proposed this as a kind of startup studio, kind of you go there for 6 months, get your business started, then move out. As soon as you have to hire someone, you'd have to move out. But we were really interested how to, it's just concrete and glass, but trying to figure out an idea of how to fenestrate this thin wall. And so we really were proposing that these plexiglass bubbles kind of push you out into the space, a little bit like, I was trying to connect to other ideas, like the suburban house, pushing you out, little thought bubbles pushing out on the side. This was, two of these projects were two of the sponsors. This was for the Architects newspaper. It was their second birthday party. I don't know if there's Bill here. I think it's happy 5 now, maybe 6 birthday. But this was when this building, which is 7 World Trade Center, the first rebuilt tower by SOM, they were given an unfinished space way up here on the 53rd floor. And we had to bring everything in a day, and we had to take everything out in a day. So the answer was, again, the expediency of plastics. So we made these sort of globe box benches that made a kind of porch out to the city. The beauty of Ground Zero at that moment was nothing else is built around, as you know. And so we had these open views to the Woolworth Building, to New Jersey. And it was actually the first time I think everyone realized that we would get those views back. They were taken from us, and those views would be given back. We used these sort of inflatable bubbles for people to sit on, and we called it on air because in a way there was nothing there, and you were up in the sky, and we would sort of like use plastic. It's sort of like thinness, thin skinness. This is a very old project. This is our first prefab project. It was kind of why we started doing prefab, because Allison Arias thought we could do it or design it. But this was an idea for an independent living for elderly. And the idea was that, in that time, 1998, it seemed like my parents were not going lightly into the night. And so it seemed like if you're going to have your midlife crisis, or I guess your last life crisis, it should be done in sort of a design. And so we were thinking of how to line the surface with something completely uniform. And so the idea would be that there's some sort of lining that would be maybe a vinyl lining, it could be a rubber synthetic, that is sort of carefree. But again, everything folds out of that wall. And that led to our version of I guess, our Monsanto house, which is funnily distorted there, but it is really distorted. But this is the Up House, which again, the Vinyl Institute sponsored the exhibit at the Cooper Hewitt, was included. But this included, you should see these panels of PVC that are 1/2 inch thick, that are translucent and rigid. The light comes through, and the idea is to line the entire interior of that as well with PVC, a kind of seamless, uniform, but also allow you to see a little bit through to the structure of what's behind. These were projects that are kind of emerging projects out of existing architectures. This is maybe about where, for one reason or another, we can't tear down the building. so we had to add to it. This involved another child being born by a faux painter and his wife, Spanish wife, and it really is like, how do you just make a mass sort of coming out of the bedrooms out of the 4-square roof and the hip roof. And another version of this was for artists not far away from this, where for another reason we couldn't tear down the warehouse, but putting a vinyl sort of, or a roofing material using a kind of cool roof vinyl, just using it almost as entire surfacing. So the roof is actually, you know, not distinguished, it's actually just the entire surface. And this was the funniest one of that series. This was the father owned a bodega, the son wanted to get him out of the house, built his apartment on top of the bodega. And so this is a sort of house that's in pieces. Each room is articulated as a different color. Again, sort of a thought about that. And this was something, again, where there's an existing wall and thermal springs and sort of just building up, again, little cabins. These were cabins for a hot springs resort. Again, sort of the same idea, just single material. This last project is sort of a more recent project where we're trying to do something where we reuse materials, and we reuse old materials and we incorporate new materials on 2 halves of this building. It's a house, it's supposed to be a $100,000 house for budget, but this idea of the free tag bag, and you all are so pleased after having made this last week that you all have bags like this, product placement. And so this is about recycling roofing pieces, vinyl, as a siding on the one side of this house. And it's a curious house. And it's really, I don't know, we use skylights as windows, you know, for budget reasons. And it's idiosyncratic kind of purposefully. And so it's almost a slug, or it's almost this kind of like, I don't know, it's ugly in a kind of interesting way for me. It's not like the up house. It's kind of trying to not do another up house. But the way we made this form is very simple. I wanted to start with a rectangular form and then just chamfer it off based on these 3 conditions of where the sun is in the sky. The reason for that is we wanted to use this new technology, which is a thin solar panel that can be glued onto the surface. So again, this thinking of like, there's no roof, there's no wall, it's just a surface. There's just maybe a roof or just an enclosure. And so using this, and also something fascinating with, is also the two-sidedness of the space shuttle, where there's this one side that has a real performance function of a heat shield. It has to re-enter. And then there's the reflective white on the other side that's like more what we know a spacecraft to be, the skin. So this other side has that material on it, and it's on the angle, of the solar angle, so that it just does pickup all day long. And it distorts the inside in an interesting way, and again, the back is almost more curious than the front because of that distortion. Okay, and this is the paradox part, if I can get this right. Now, plastics in art, I was looking, I don't think there's enough plastics in architecture. And what's so interesting, Monsanto House gets torn down after 10 years, probably because, as Theo said, it's probably yellowed, or it looked old after 10 years. It was out of fashion. But some artists are using sort of synthetics and plastics to get realism. You know, almost here, Ron Milk, who's trying to kind of like almost supersize the birth. And it's almost a shock value. But what's interesting to me is the use of materials to take it out of its context. Oldenburg was early to this, his soft sculptures. Things we know are hard. Well, we know that's vinyl because it's soft. I mean, we know it's vinyl, but it's a toilet, so it's not a toilet. And this is what, to me, is a very interesting paradox, and why these are perhaps successful, is that they hold those 2 things. They're wrong, but we know why they're wrong, because we recognize what they are, and they're just wrong, you know, but they're made out of vinyl, you know. The vinyl makes them wrong. The vinyl's being true to its material, but he's using the wrong material to sculpt it with, to be realistic, let's say. And this is actually, you know, as I started to investigate this is a real issue for collectors and museums that actually have plastic in their collection. AXA is an insurance company. The only ones really concerned about this in a sincere way is AXA did a manual about how to conserve or what the problematic is with plastics as they age. And I think this Nam Gabo was really interesting. He would reconstruct his pieces that were some of the first uses of a kind of plexiglass, but it was a cellulose, I guess it's a cellulose acetate, which was different from nitrate, which was the very flammable for film spools. But these would, he got very angry in the 60s that the curators at the Philadelphia Museum of Art were not taking care of his work. And he offered to remake the work for $10,000 and to fix it as it is in its original state. And they turned him down and went to someone else, which I guess would be considered a conservator, right? But when should the artist be able to remake his work and not be called a conservator? And when is a conservator an artist is what starts to get at issue here. But he's also using materials before you know their life cycle, before they're new, and so the way you're finding out is the hard way, is that they are deteriorating. But I think the deterioration process is something that's perhaps useful for the artwork and not something to be remade. Dwayne Hansen in the 70s did these sort of like Madame Tussauds of ordinary people, no one famous, and made them again so lifelike and so real. But what's so interesting about them is without any conservation, they begin to become a time capsule. And even this bag, I don't think there's a Grand Union anymore. Whatever was printed here suddenly is dated. All the plastics that you have to worry about are the formicas. There's aging that's happening to this piece, even though it's like a snapshot from 1970. And even the clothing, the fashion will change. But what's a little bit interesting is that they only work if they look like people. But when they start to look like cadavers, where you see this dishwasher's ear has turned purple due to leaching out a plasticizer coming out of the material, it takes on a new meaning, right? And I think actually culturally it's very interesting. And it's again the conservation of all these other materials as well as just the actual body. And we saw this earlier, these processes artists work in, and I think one artist in particular to look at, I think is really interesting in terms of how she accepted or embraced the fact that plastic would not be 400 years, that it would degrade. And in fact, she actually says her aim was, I wanted to get at non-art, non-conative, non-anthropomorphic, non-geometric, nothing, everything, but of another kind. Vision, sort, from the total, other reference points, she wrote in 1968. This is a picture months before she died early of a brain cancer. She says this, which I think is a very interesting thing. She says, some of my work is falling apart. If and when I can repair it, I do. If not, so what? They are not wasted. I went further in the work that followed. But ironically, she dies with leaving a body of work that is unstable. And I think the unstableness of her work is probably true to her intention. And there's a kind of darker side to her use of plastic. It's not the optimistic house of the future, or even my work earlier, where we were like, excited about how we can go into space and use it. And even we take those things down, they're temporary. These become conservation issues, but what do you conserve? Do you let them deteriorate? Is that the artist's wish? And therefore, that was an experiment that just fades away. And I think that's a good question for discussion. I'm looking for an equivalent architecturally, and I'm wondering if there's like a molting that could happen with architecture. If we like have skins that just as they are used, that might be my next series of the skin, just like they just drop away, like every 7 years, and a new skin is revealed. And I mean, the closest I can find is this sort of image of an early plastic house that seems in some way to hold that same sort of Hess sort of authenticity, that it somehow is not exactly perfect, but the deformations and degrading are acceptable. And that's my talk. Thank you.
Good morning, ladies and gentlemen. Being in that conference, I have to admit at first that I'm not an architect and I'm not a plastics engineer. During the preparation, Michael Bell found out that I'm a lawyer by education. So my attempt to become an expert on communication and plastics was not accepted. He wants that I play the role as an attorney for polymers, and I do that beginning with my suit. So, this is my agenda. I'm presenting the case plastics against public perception. What was the history of this dispute? How did the industry defend its product? And what is the judgment? At the beginning of my presentation, I want to show you two national monuments. Probably you know this building in Dessau. And both buildings were recently renovated. And in Dessau, they used the original material, for example, steel for windows. And in this plant in Pirmasens, the authorities allowed plastic windows to be installed because the difference what was not visible. And I think this is a nice story. We heard already that from Mark Wrigley yesterday, polymers are an underestimated material, and I think this story underlines that. Between the building and the renovation of this plant in Pirmasens, we have about 80 years, an incredible increase of the consumption of polymers, but that was not visible. At the beginning, another monument, this is the headquarters of Henkel in Düsseldorf, where one of the first PVC flooring was applied. The use of the material grew, for example, by applications in the medical sector. The blood bag was introduced in the Korean War. And another invisible product since the 30s in the United States as well as in Germany and Europe, pipes were installed in the underground, again, not visible. I use a similar photo but tell another story, or just remind you what we have heard already in the morning by Craig, this unbelievable success story in the 50s and the belief that plastics could be the solution for everything in the future. But after that, what we would call in German a hype, there was a big public debate and a big many objections against polymers, with a slogan in Germany, natural fibers against plastics, Jute statt Plastik, which was very common, and it was a crisis for the plastics industry in different countries at different times. That is strange, but the period happened everywhere. And we had this in the 80s in Germany, we had this about 2004, 2005 in France, and we have that and there was a book called The Plastic Bag War, so emotional was that discussion. And we have this in 2010 and 2011 in Italy. How did the industry react? The defendant investigated a lot to find out what of the allegations is founded or what is not founded. The recipes were changed. We replaced harmful against less harmful additives. We investigated the benefits and the limits of the materials. So I'm totally in line with what Jan Knippers said. The outcome of the investigation is not, there is nothing wrong with the material. The outcome is that we now know the benefits and the limits better than before. And the main task is to increase the dialogue between designers and architects and the industry to better understand the needs and the opportunities, the needs by the architects and designers and the opportunities of the material. What we also increased were recycling schemes, and the public discussions everywhere started with plastic bags, because in this case plastic was visible in the landscape, and the answer is to recycle material even in applications where it is not visible. Plastic windows were invented in Germany in the 50s, and we started this, the big sales started in the 70s, and we started recycling in the 90s with several plants now on an industrial scale, no longer pilot plants. Here is an example in Thüringen, close to Weimar. The outcome is raw material, which again can be used for plastic windows and is used. And it's also done in the United States. You may know that the gates here in the Central Park were made from PVC as well, and Christo wanted all materials to be recycled, and these gates were recycled. I forgot the name of the place. I think it was in the neighborhood of Philadelphia. And again, you get regranulate, which you can again use for pipes or other material products. This is an example of Japan, where this is a roof to give shade made out of recycled PVC. What we also change is communication. And in this case, we organized a meeting between the artist, Anish Kapoor, who designed this sculpture in the Tate Modern, and we organized a meeting with architects from Germany and journalists with the artist to understand the material and why he has chosen the material. And of course, not to forget experts from the industry with the other groups. We also invented a magazine which does not promote the technical benefits, but tells success stories to make people interested in using PVC in this case. And we organized seminars where I met, among others, architects like Konyk. It started in Berlin, and as a result of a series of seminars, we published this book in 2005. It's, the title is in English, Plastics and Free Forms, which relates to one of the benefits of plastics, that you can make many different forms out of it. And we produced another book which shows one of the benefits. It's the efficiency of the use of the material. With a very small amount of polymers, you can produce outstanding constructions. And the result, and this is one of the results, is that we are now an accepted part of the society. You all may know Mr. Töpfer, and this is a lady from the Wuppertal Institute in Germany, prominent as experts on sustainable development. Other result of this new evaluation is that we now are better in producing design which look like wood, for example. or we improve the quality of the pipes to make them an important part of the surface infrastructure. We don't need external screws. We can put the screws in the pipe to connect the pipes very sufficient and perfect. This picture I have already shown 2007 in our seminar in the AIA here in New York to demonstrate for one application we have a big variety of compounds. We can make a film transparent or not transparent. It can be UV resistant, it can have different fire behaviors, it can have different colors, different surfaces, and so on. And the challenge is the dialogue between the architects and designers and our industry to learn from each other for what purpose you can use what material. This is just an example for transparency, the possibility to give colors, all the colors. And one of the outcomes of this new evaluation of plastics is now architects use it in a visible way. And one of the first examples I have seen in Germany was this roof in Stuttgart. You see that from there. When the task for the architect was to construct a roof on an existing football stadium because of the World Championship on athletics, which were organized in Stuttgart. Afterwards, it was used in the football championships in Germany, in Korea, and now in South Africa. You can use it for non-permanent buildings, like here in Oslo, or when the Pope visited Germany. This was a cloud to hide all these technical equipment. Famous architects like Van Koolhaas use plastics, and others, of course, it's just an example. What is very important also is just a reminder, today we can produce big structures with polymers. For example, these blades for the windmills, they have a core of PVC foam, and they are enormous, big. This is a person here, just to give you an imagination. Some of us came from Europe by an A380 Airbus. It's constructed to a big extent by plastics. And we investigated new applications. PVC film is not something really new, but the better people know about the benefits, there are new applications. And in this example, it is used to substitute paint on boats. And it does not save a lot of weight, so the boats can be faster. It has a very smooth surface and allows to protect the boats without harming the environment. You know the debate on TBT, to protect boats from shells. And the same technique we can use to customize the decoration of cars. You may have seen this example from BMW. This was made by Jeff Koons. And we can also build customized houses. This is from the Up House project you have seen already. And I have taken this title from a catalog we produced after a students' competition. One important point of polymer plastics is you have the choice. You can make mass products in series, or you can design individual, as we have seen in the previous presentation from Knippers. We are in a conference about plastics, so please concentrate here. What I want to show with this picture is plastics also allow to produce in countries with high salaries. These hangers are produced in a very small firm in Cologne with about 35 people on a very sophisticated technique. They are produced in Germany, shipped to Asia, and come back with the textiles from there, because we can afford to produce them in our country, as it should be possible in the United States as well. My last slide, you have to read from the right. It's a funny story, I think. At the beginning, plastics were a substitute of other materials. This is a branded glass bottle, and when the material changed to plastics, they used the design of the glass bottle. And 4 years or so ago, I gave a presentation in Vienna, and I saw this glass bottle, which tries to imitate the design of this plastic bottle. In this case, the folds have the function that you can press the bottle together to reduce the volume for the waste. And in this case, the folds have no function. It's just imitation of this design. Thank you very much.
Well, I want to thank the Vinyl Institute and Michael and all the people who did so much work to get this event together, and all of you for being patient ahead of time, because I am not a lawyer, I am not an architect, I am not an engineer, I am a scientist. And I have to say, this is actually the first time that I've ever had to speak in front of a room full of architects. So excuse me if I'm using different words and saying things differently. I run an institute with the mission to support fact-based environmental decision-making. My own background is that I'm an oceanographer with expertise in ecotoxicology and biogeochemistry. So that's the study of how things move around in the environment and what they do when they get there. So we do a lot of work with industry because we know that industry is the only part of our economy that has the resources to fix the sustainability issues we're dealing with. Most of what we do is life cycle assessment. Life cycle assessment is the science of measuring the environmental performance of products and services over their lifetime from cradle to grave. And the American Center for Life Cycle Assessment is our flagship program, and it is the professional society for life cycle assessment for the U.S. We do annual conferences, we certify life cycle professionals, we do all the sorts of things you would expect a professional society to do. Come to our conference in Chicago this year. This is what life cycle assessment is. Here's a pointer here. Yeah, okay. Life cycle assessment is a systems analysis methodology. What it does is it looks at a product, usually an industrial system, but it could be a service, it could be anything, and looks over the life cycle, starting with raw material extraction, going through every step until the point where the product is taken and thrown away. And it looks at the inputs in terms of materials that are brought from the environment and energy that's taken in, and it looks at the outputs, and that's basically the pollution. And then it normalizes all that to industrial system, the function of the industrial system or the function of the product. It's basically a fairly new science. The first life cycle assessment was done about 40 years ago on plastics, as it happens. It was done on Coke bottles when they were thinking of moving to PET bottles from glass bottles. And part of the reasons that happened and the part of the reason we have PET bottles is that those early assessments showed that PET was more environmentally friendly than glass. Once you've done an analysis that looks at the inputs and outputs, then what you do is you calculate all the environmental impacts. So climate change is always calculated when you do a life cycle assessment, and is now what we think of as a carbon footprint. So all life cycle assessments give you the carbon footprint. They also give you the environmental impacts, the other environmental impacts of the product. So I think this night and day and night, I represented the U.S. in negotiating international standards on how to do these sorts of things. And there's times when I'm tired of them, but I still think it's really interesting to see what comes out, because more than anything else, what I think of life cycle assessment is a myth buster. It makes you really think about things holistically. It makes you re-examine your assumptions about what's good and bad about a product or a material, and it helps you make a better decision. Here's a fairly thorough list of the things you might want to measure with a life cycle assessment. There are standard methods for doing all of these calculations. So I want to talk very briefly, well, maybe not so briefly. I want to talk about the system function. We've heard already this morning about repairing statuary. That was wonderful, that study. We've heard about houses of the future and using plastic for them. We've looked at pictures of beautiful old buildings and very interesting new buildings, and we've looked at buildings that are do more than just hold people inside of them. They do things like provide energy. I love that design for the whole wall being made with solar cells. If I were to do a life cycle assessment on any of those projects, the first thing I would have to ask myself is, what is the function provided by that project? It is the key concept inside of life cycle assessment, and it allows you to compare product A to product B, plastic versus wood, steel versus fiberglass, and come up with a real understanding of the environmental impacts of both of those choices. So typically when you try to get a look at the function of a product, you would say, what does it function in terms of what's the quality it produces, how much of it produces, and what's the time range over which it supplies. So there have been probably hundreds of studies of drinking cups, and whether you should make them out of ceramic, or whether you should make them out of plastic, or whether you should have them plastic that's reusable versus plastic that you throw away. Everybody does these kinds of studies, usually while they're still in college. But it's very important in doing these studies that you look not just at, it's a container, it's a drinking container. You have to say, what kind of a drinking container? So you could say, this is a drinking container that's used for hot beverages. It's 12 ounces in size. And we're going to assume that it supplies the drinking container for a university for a year, all the students' use of hot beverages. And what this does is it allows you to compare the steel container that you give the student their first year of class or their first day of class to the plastic containers that they throw away every meal they go to something in between. And as I said, there have been so many different studies looking at this, and the results are, it depends. And this is very often the outcome you come with a life cycle assessment. It depends. In this case, it depends on how clean your electric grid is. So if you have, and also on whether water scarcity is an important issue where you are. So if you're living somewhere where they have a very clean electric grid, and they have lots of water, then the very best solution for you is to have ceramic mugs that you use over and over again. I live in the Pacific Northwest, that's the right answer there. If you live somewhere where water is a problem, and you have a high coal-powered grid, then throwaway plastics are the best answer. So a well-done study will tell you not only whether one thing's better than another, but it will tell you why something's better than another. Important concept, I think, because we have not really talked about function today, but I think it's essential. Here's some examples of functional units. So if you could say a square meter of windows in an opening for 70 years. The average commercial building in the United States lasts for 70 years. 100 square meters of interior paint for 5 years. 1 billion liters of water supply that meets the quality standards for health and environment. Or you could look at a ton of plastic resin and say, what's the environmental impact of that ton of plastic resin? So we've been talking a lot about the characteristics of plastic, and these all feed into doing a life cycle assessment. So we know it's malleable, it's chameleons, you can make anything out of plastic pretty much, and people are thinking of new and better ways to make things out of plastic as we stand here. It's very effective, otherwise we wouldn't be using it. It's pretty long lasting. It's kind of interesting, I always feel like I have a dichotomy when I'm talking to people about plastics. On one hand, you have the conservationists who are saying, oh my God, it's turning color, it's getting brittle, it's not lasting forever, it is not stone. And on the other hand, you have people who say, you make plastics and they last forever, you can't ever get rid of them. They're gonna be out in the middle of the ocean forever and we're all gonna die because of that. I really don't understand, well, I do understand. It's a very complicated topic. There are many ways to look at it. But typically plastics take little maintenance. I'm very interested in the issue of plastics in the marine environment. I guess is not surprising. But using vinyl paint in lieu of using butylated tin paint sounds like a brilliant idea to me in terms of reducing toxicity of man in the ocean. We know that plastics are generally not very good at weight bearing. And what's happening then is that there's all those clever engineers that are finding ways to make plastics be better at that by adding fibers and what have you. And we also know they're inexpensive. So I think those are all important things when we think about this, because any decision we make about using plastic or not using plastic or modifying plastic, we need to think holistically about it. And not only think holistically as I think about in terms of its function and its environmental impacts, but also holistically in terms of its social benefits. So plastic is cheap and it works. And so here I'm going to take my little switch because I am an NGO, and part of my job is to try to make people think differently and think in bigger terms. So I just went online and got estimates of the cost of a plastic versus a conventional product. I got vinyl flooring versus wood flooring. Vinyl flooring lasts for about 30 years. It costs about $250 a foot installed. You can get a range around that. Wood flooring lasts a lifetime. I'm not sure what people mean by a lifetime, but it's $9 a square foot. When you do a life cycle assessment of a building, what you would do is you would say, here is the building when it's new, and we know it's going to last this many years, and we calculate the environmental impacts of all the things that you do to that building until it's done, until you throw the building away. So that means what you're saying is, I have a building, and oh, by the way, in the United States, the average residential building lasts 61 years, plus or minus 25. I love that statistic, and that actually came from our last year's conference. Somebody gave a wonderful talk on it, so I put the reference there for you. So you would say that this vinyl flooring, you would have to replace it once during the life of the building. So during the life of the building, you would spend $5 a square foot for vinyl flooring as opposed to the $9 a square foot for the wood flooring. Okay? Another example of plastic versus conventional is PEX pipe. So that cross-linked polyethylene, it has a 50-year life. I bet you that it probably lasts for 60 years. You wouldn't have to change it during the life of a building. And you can get it for 40 cents a linear foot. And your alternative is copper pipe. Copper pipe lasts a lifetime, and it's almost $6 a linear foot. As it happens, I know a lot about the toxicology of copper and polyethylene, and I can tell you that you don't have any toxicity issues with the polyethylene, and you have a lot of toxicity issues with the copper pipe. I give a class on green buildings using a life cycle approach to people who are maintaining green buildings, plumbers and carpenters and electricians. And the plumbers always hate me when I tell them not to use copper because they know copper is the best. I'm here to say, from an environmental perspective, plastic is the best. Hands down, this is one of those ones that's not maybe this way, maybe that way. Always, it is better. Okay. And rather than give you a whole bunch of data on different plastic studies, I just wanted to summarize here that there have been hundreds of studies of PVC alone, and also hundreds of studies of other kinds of plastics. And what they find out systematically is that the plastics are pretty equivalent in terms of their overall environmental impact. And sometimes they're better than conventional materials, and sometimes they're worse. It depends on what you're using them for. So when you do a life cycle assessment, it's important to know what the product is being used for. But just as recently as last year, there was a study out of the University of Pittsburgh that was ranking materials using life cycle assessment and comparing it to green scoring ranks. And what they found was, you know, there's not a big range in environmental impact, and PVC, which tends to be vilified, is right smack in the middle in terms of environmental impact. So again, this is one of the cases where I often have to say this, you know, materials are pretty similar. The choices that you make are probably not going to be about, I like this material because it's more environmentally friendly. The choices that you're going to make are going to be aesthetic choices, or they're going to be functional choices. But for the most part, certainly for plastics, the decision will not be one on environmental impacts. I'm doing a project right now to develop eco-labels, life cycle-based eco-labels. They're called environmental product declarations for windows. And I took this picture when I was in Italy last year of this building that was built in 1925, and it has all kinds of windows in it. What's interesting to me is it has windows that have glazing, and it has windows that don't have glazing. It's still a window though, isn't it? I mean, architects wouldn't know, okay. You can help me here. Okay. Somebody mentioned the Parthenon. This is a shot in the Parthenon. It has the same kind of window. This is like a 2,500-year-old window. This is just the same as the window from this building that was built in 1925. So in terms of permanence, hey, holes in the walls are pretty permanent. We've had them for a long time. They work pretty well. But in terms of the life cycle of a building and how important the windows are, when you do a life cycle assessment of the building, about 85% of the impact of the building happens during the use phase of the building. It's caused mostly by water and energy consumption, and about 85% of the carbon footprint comes during the use phase of the building. So the most important thing for a window to do is to keep out the heat and the cold. And that's why it's not so good to have those windows that have metal around them, because the metal acts as a way to move the heat through the building. and you want it to keep it out or in, depending on whether you're hot or cold. So, I'm not advertising these guys, but there's a company out there called Super Insulating Serious Windows, and if you Google Serious Windows, you'll find them. And what they've done is they have developed windows that are really good insulators. And the way they've done that is by putting plastic films on them. Right? So yeah, they've got the air pockets between layers of glass. But the real winner, and the reason why they can get above the Energy Star ratings to their beautiful green windows, is that they're using plastics to do that. So I would posit that this use of plastic, which is invisible, I mean, we've been talking about things that are visible and not visible. You don't see the plastic, but it's saving you. And I don't know whether you could recycle this stuff at end of life. But since 85% of the impact comes during the use phase, then maybe it's not that important that you have this thin layer of plastic that you can see through, but that is reducing your heating bills by 20 or 30%. Okay. And so I'm going to be an environmentalist and remind you that people are really good at making babies, and this is what the world population has been doing since a couple thousand years ago. I feel great urgency that we need to solve our problems now about how are we going to take care of these babies when they grow up to be needing windows and doors and housing. Because there's old ways to live, you know. This is a picture in a Maasai village, and these kids are leaning against the wall of their preschool. There are no windows in this building. And it's made out of mud. Actually, it's made out of manure. And it's intended to fall down in 10 to 15 years. But they've been doing it since the Stone Age. And here's what happens to have post-industrial Stone Age is what I call it. We have engineered materials, but it's a slum. And I think the important question to ask ourselves is, are we interested in making beautiful monuments like this one, which is a building for the ages, or are we looking to build decent housing for people now? And doing that means that, well, a really good tool for doing that is to use those cheap plastics. It's not the only way to do it, but I think it's an important thing to think about. Thank you.
In the interest of time, I first want to thank everyone, thank all the speakers. This morning was fantastic. We're going to have time to, and I'm Ben Preusker, the Director of Events at the school. We're going to have time for questions later in the day, but we have a very tight schedule this afternoon. We have a venue change, if anyone hasn't noticed, for the Michael Graves honorary keynote is actually across the street. So I'm going to say that we're going to go take a break, grab a sandwich, get some lunch, and be back here as close to 2:15 as we possibly can, and we will save your questions and have some time to come back to them later. Thank you.